For a fish to be buoyant or float, it must be able to maintain a balance between the force of gravity and the force of buoyancy by manipulating its own overall densities without significantly increasing its mass. There are three ways for fish to maintain their buoyancies depending on the type of living environments which they reside. Bony fish typically have swim bladders which are filled with air or oxygen to help fish achieve this. Fish with no bladders, such as shark, has to rely on continuous forward movement along with angled fins, sometimes oil, in the liver to stay floated. A swim bladder is simply a expandable sac, similar to a human lung. Fish with open bladders, typically freshwater fish, often need to reach the surface to feel the air through their gills and their mouths. Fish with closed bladders pull air out of the connective blood vessel to stay buoyant, and the air in a circulatory system comes from gills through the air in the water. Now, closed swim bladder and no bladder concepts are extremely difficult to achieve through mechanical designing. Therefore, our main focus of the project is to simulate fish with open swim bladders, creating a buoyancy ladders which demonstrate the concept of simple fish buoyancy.
The prototype of final product displays the model of a typical fish. The setup will allow the consumer to understand how buoyancy force is related to a fish's bladder, which is common for younger age curriculums, and it even demonstrates actions that are hard for humans to see up close. This can be shown by forcing air into the balloon and allow this fish silhouette to float vertically and vice versa. The size of a setup is 18.30 inches in length, 10.63 inches in width, and 23.78 inches in height, which can be easily transported by car. The amount of water that can be filled into the setup is approximately 15 gallons, which is enough water to demonstrate our product's functionality. The product only needs one user to set up the whole device by just connecting a few user-friendly parts. The product has a maximum of one user input that can engage with a small audience, which is ideal for a classroom scenario. The product can be easily stored during downtime seasons and doesn't require frequent manufacturing maintenance.
Our first experiment was to test whether the buoyancy of the prototype with two balloons was sufficient. We discovered that the current setup was unable to fill two balloons at the same time, but learned that one balloon provided sufficient positive buoyancy. As a result, our second test was determining the ideal mounting location for the prototype to sit level while at neutral buoyancy. By sliding the air bladder tube left or right in zip ties, we settled on an ideal mounting position shown in the photo. Combined with the guide tubes on both sides, the prototype can stay level during operation. The final experiment was to determine how much weight needed to be added or subtracted for the current design to sink when deflated, float when fully inflated, and remain neutral in between. We discovered that no weight needed to be added or subtracted for the prototype to perform optimally in all situations.
From the experimental data, the team communicated with the prototype and learned several things during the prototype developing. For example, an actual fish bladder has two balloon-like airbags. However, the team cannot mimic the double balloon feature in the prototype design, because without muscle control, the two air balloons cannot be filled up at the same time by the reason of elasticity difference. Also, in water, the center of mass has a significant effect on the model rising direction. The team adjusted the location of the balloon on the prototype by experimenting vertical stability tendency, and the team added a guide slot design to make up the horizontal balance control. Lastly, the amount of air that has been pumped into the balloon will affect the rising speed of the model, which is an important factor to actual exhibition and demonstration. Thus, the team designed an air volume control to in between the pump and the balloon. However, due to the limitation of material and budget, the design isn't realized on the actual prototype. Overall, the prototype was designed successfully to address the major functionalities.
The prototype designed by the team meets the Center for Aquatic Sciences needs for a model that emulates animal behavior on command while also incorporating variable user inputs and outputs. Utilizing the applied science concept of buoyant force, the team's prototype demonstrated the natural science function of the swim bladder, an organ which is present in a variety of fish species. The prototype developed by the team meets specifications by illustrating a concept in a manner suitable to 6th to 8th grade students. It can also be set up and operated by a single person, stored in a small and intuitively packaged container, and the only consumable is generic latex balloons, which will also last through multiple experiments. The cost of materials in developing the model was also well within budget constraints. The further development of this model should be pursued by EduRob, as the prototype was successful in proving its feasibility as a finalized design. In conclusion, the bladder ladder provides a cost-effective, convenient, and relevant method of teaching the science of buoyancy and swim bladders to junior high students.